Hey, what's up, guys? Welcome to Apache Storm's certification training, and I welcome you all to Edureka. I'll try to make as much engaging and fun as possible, and we will have lots of live coding sessions, demos, and assignments. Hope you all have fun. Right, so what are the objectives? Well, after completing this, you should be able to know the basics of big data and Hadoop, and if you already know it, you'll be able to recall it. And you will be able to understand what is batch and real-time analytics of big data and how do they differ. We'll see what are the shortcomings of Hadoop, and we'll understand what is Lambda architecture and why do we need it. You will be able to develop a basic understanding of Apache Storm and its components, and this will act as an excellent starting point for writing Storm topologies in future. And I'll also explain the use cases and key differentiators of Storm, why it is preferred over some of its competitors, and why you should pick Storm, and where does it fit and where it doesn't. So let's see the definition of Storm. So Storm is an open source computing system used for processing real-time big data analytics. Wow, that's a pretty convoluted statement. So let's break it down a bit. So first, let's understand what big data analytics is, then we will understand what real-time is, and then maybe this whole statement will make more sense. So what is big data? Big data is anything where you have huge amount of data. So as the definition says, big data is the term for a collection of data sets which are so large and complex that it becomes difficult to process them using your regular database management tools. Like you have your MySQL, Postgres, and Oracle, and any other traditional data processing applications that you have. And the challenges are plenty. I mean, you cannot capture that amount of data when you have terabytes and petabytes of data produced every maybe day or month. It becomes really challenging to capture that data and the curation of that data and the storage of that data. Because most of the data is unstructured, you cannot store that type of data into your regular on-hand databases. And the sharing of data, because the data is in terabytes and petabytes, you cannot share or transfer the data over the wire easily, and you cannot analyze that much amount of data because you cannot bring it all into memory. And most of the data is unstructured in big data world. For example, you have log files. Log files will have so much amount of unstructured data. I mean, almost 80% of the logs that we have are not used for almost 80% of the time. So you can see how we have so much amount of data which we don't need, and it's very difficult to extract some meaningful data out of that unstructured data. So let's take an example of a big data system. So you have your stock markets which generate about 1 terabyte of new trade data per day to perform optimal stock trading analytics to determine trends over optimal trades. So people are buying and selling stocks all the time, and if you start saving all of that data, because the data might be very useful, and as we will see, and you can extract so much information out of it that might be of use to you. So how can you use that data once you have collected it? There are basically two aspects of analytics. One is discovery. That means you want to identify interesting patterns in the data, whichever makes sense to you. And another one is communicating. You want to provide insights in a meaningful way to your upper management so they can use those insights into some productive work. And the goals of analytics are to increase the sales, of course. That's the primary goal, but also to make your company more efficient in terms of cost saving and people saving. So unstructured data is exploding day by day. You can see the graph here. We started collecting data after 2000 mainly, but after 2010, the data exploded at an exponential rate. And that is one of the reasons why machine learning is picking up so much, because it requires lots and lots of data. And you can see the numbers here are pretty appalling. 2,500 exabytes of new information in 2012 with internet as primary driver. And digital universe grew 62% just in 1 year to 800k petabytes, and it will grow to 1 zettabytes this year. So of course the number are pretty dramatical, And relational data, of course, is not increasing at that much pace because most of the companies are moving to NoSQL databases. And secondly, there is a lot of unstructured data. You can see with big data analytics, we are targeting this orange zone, that is your application data. So IBM has its own definition where it says if you want to identify that the data is big data, it need to satisfy 3V properties, which is volume, velocity, and variety. Volume means you should have very huge data. Velocity means it should be produced at a very rapid rate. It should not happen that you do have large amount of data, but it was collected over last 20 years. It should be like you have produced huge volume of data at a very fast rate. And then your data should have a variety. If your data doesn't have variety, if you have a very plain rows and it is not unstructured, you can probably put it into any NoSQL database and start querying it. So unless your data is unstructured and you have lots of varieties of data, that data isn't considered big data. I'd say when you have your data, you have mainly two types of analytics. One is business intelligence, where most of the data will have multiple dimensions and you will try to find insights using those dimensions. And you will even do machine learning using these dimensions. So for example, you will have dimensions like this stock price was increased by this much at this time. So you have three dimensions in your stock data. That is, one is stock symbol, another one is percentage change, and third one is time. So now you can play around with these dimensions, like what was the average increase in banking sector at 2 p.m. yesterday? Or if you had e-commerce, you can say like which shoes were sold most in month of May in Delhi area. These kind of analysis can simply be done by writing a simple program which aggregates on your data and finds out these simple business insights for you. Another one is predictive analysis, which is getting very popular these days, and it works on statistics and machine learning, so you can predict user behavior from it. It includes things like clustering, classification, and linear regression, and you can say things like these things were frequently bought together, like you have on Amazon, and you can say like this phone and this screen guard were frequently bought together. So let's talk about what is batch and real-time processing. Let's first talk about batch processing. So we just saw that batch data processing is an efficient way of processing high volumes of data, where a group of transactions is collected over a period of time. So data is collected and entered, processed, and then the batch results are produced. Batch data processing requires separate programs for input, processing, and output. So an example is like payroll, which usually occur on monthly cycles, and something that might occur on days as well. It doesn't have to be monthly only. So other example can be you're trying to get some consumer trends over the past few years. So past few days maybe. So you can ask questions like which shoes were most popular among adults in last 30 days. So these all are batch processing tasks. So let's see what real-time processing tasks are. So in real-time data processing, the data is coming continuously and you are processing and outputting the results of that data. So data must be processed in a very small time period. So for example, you have radar systems, you have customer services, and suppose when a shopper hits the ATM, you need to update his bank account immediately, and it should be so close that the customer doesn't even notice the delay. So you're processing the events as they are coming in. Another very popular example that you will see everywhere is to analyze your data within a rolling window. So suppose if I ask what were the most popular hashtags in last 10 minutes, of course, you can do a batch process and give that to me. Suppose our batch process is very fast, it doesn't take any time, and you get the most popular tweets in last 10 minutes instantaneously. But the next minute that data is stale because you got new data in, and last 10 minutes, the new popular hashtags in last 10 minutes are now changed. So what you have is stale. You need to continuously keep updating the count of your hashtags as soon as the data is coming in. For that, you cannot use your batch process. You need something that is processing the data as soon as the data is coming in and giving you the live view of data all the time. In that case, we will always use real-time processing. So let's see what are the advantages of batch processing first. So it is ideal for processing large volumes of data, and it increases efficiency rather than processing each record individually. You can write your code much more efficiently if you know that data will be coming in batches rather than one at a time. And it can be done or processed independently during less busy times. Of course, at daytime, your servers are busy serving the live traffic. If you are trying to do real-time analytics, you'll need to buy new servers. But if you're using your batch servers, you can free up some of your servers at night and use those machines to batch process your data. Let's see what are the disadvantages. The only disadvantage of batch processing is the time delay between collection of data and getting the result. So as I gave you the example of rolling window, of course, that time delay is not acceptable. Let's see what are real-time processing advantages. So advantages, there's no delay in response. Of course, it is very, very useful in social networking. So how can you use this in social networking? Pick your own big database and then you can measure the immediate impact to your site traffic from any social media. So if you have posted an ad on social media, or you have launched a new blog post, or you have tweeted something, or you have put some reward on liking or commenting on your page on social media, you can measure the impact real time. And of course, knowing this information translates to a better conversation and more effective online campaigns. Of course, the SaaS companies, that means software as a service companies, which are serving many clients at a time, can measure user behavior and act upon it for improving customer satisfaction and conversion rates, which means immediate increase in revenue. And that is what most of the companies care about. Financial services. So determining in real time whether your portfolio is losing money or there's a fraud in your system, you can prevent disasters before they occur and not after the damage is done. And secondly, you can have sentiment analysis, or you can correlate 3 or 4 parameters to give you live insights into the market to maximize your profit. So let's talk about a real life need for real-time analytics. So your problem statement is you need to find the total number of page views of Edureka's blog over a range of time. So the range can be, give me page views of this particular blog of last one day. So Google Analytics can provide this information to you, right? So example, for a particular day, the data can look like this, where these are number of views on each type of blog. These are the percentages of total number of views. What is the challenge here? Querying huge amount of historical data. Of course, as soon as you get the event of viewing a blog, you put it into a log, right? You possibly won't keep viewing events in your relational database. So the problem is, if you are putting everything into your logs, querying that huge amount of historical data is going to be slow. So if you have all the data and that data has become of petabyte scale, suppose you are aggregating over last 1 year of data, that will be too slow, right? So what you want, you want to aggregate the data so that you don't have to save all the data. So you will pre-compute the data and then query on that. So for example, Google Analytics might have to keep the historical data aggregated for each hour as pre-compiled view. So suppose this is all your page view data, you will keep it into a database like this. So this data has been aggregated. So for this particular URL, this was the hour of the day and this were the number of views for this blog, and maybe you will have date as well. Now when you query, you just need to aggregate on all of these and you will have your data. Of course, you can do this thing using your Hadoop batch process. You'll run a Hadoop batch job on all of your data and then you will pre-compute the views and then you can query that data. But what about the data generated that was after the pre-compiled view? So suppose you ran your Hadoop job yesterday, you won't be able to see the data that you have today. So what about that data? You can keep putting your real-time data into an application. Just forget about this ellipse as of now. Just think of this as a black box application. You are putting your real-time data into this application and you are computing real-time views on that data, and then you are saving it to database of your choice. So you'll need to do two things now. You are sending your live data into your Hadoop job so that you can pre-compute and run the batch jobs daily. And then you will have one more application, and that will pre-compute your real-time view, that is today's view, working on events as they come in. And then when you query, you can merge these two results and you will have the complete information in your query. So this sort of architecture where you send your data to your batch jobs and to your real-time jobs is known as Lambda architecture. And it is because this thing, it looks like a lambda. As you might have seen, a lambda is a Greek symbol which looks like an inverted V. So this is what a lambda looks like. So Nathan Mars is a guy who was the inventor of Storm, invented the term Lambda architecture. So what you will do is that every time your new data is coming in, you will send it to two places. One is to your batch layer, another one is to your speed layer. So batch layer has two functions: managing the master dataset. So all of the data that you write into your batch layer will be immutable. That means you will just be appending to same files again and again without disturbing the data you already had. Whatever the softwares and processes and MapReduce jobs you will write on that master dataset, you will never ever change your master dataset. You will just read it, compute results on it, and save it somewhere, so that if anything goes wrong at any point of time, you can just rerun your job and you will get the exact same data again. This property is known as idempotent, that doing same things again and again on a particular piece of data will produce same amount of data. Once you have produced the views after doing some computations on your master dataset, of course you can query these datasets in a low latency ad hoc manner. Now let's talk about speed layer. So the speed layer compensates for high latency of updates to serving layer and deals with recent data only. Speed layer will only work with the recent data. As I told you about the rolling window, your speed layer will only work on the data that you collected after the pre-compiled view, so that you don't have cross-cutting data. So now you have a real-time view which has, suppose your job was ran yesterday at 12 p.m. You have data up to last 12 p.m. here, and the new data after 12 p.m. is here. So whenever you want to query now, your query will merge the results from last 12 p.m. from here and the results prior to that from here, and you will have complete information again. Alright guys, so now that we have seen what is batch processing and what is real-time processing, let's see what is Storm and how does it fit in. So as the definition says, Storm is a distributed, reliable, and fault-tolerant system for processing streams of data. So anytime you need to process your real-time streams to produce meaningful data within a sub-second latency, Storm is your guy. So to understand Storm, let's take a simple analogy. Suppose you are running a company and you are interviewing people for some particular job. So now your job is to filter candidates out of thousands of candidates that you are receiving. So what will the scenario look like? You'll have a main gate via which your candidates are entering. Then you will have a given room in which 4 panelists are sitting. So first panelist only checks your name and checks your resume, that you have everything that you need, and then he sends you to the next person. So this guy only takes up 1 minute of your time. So now the next guy takes your technical interview. He takes, suppose, half an hour of yours. Then you have a third guy, which is an HR interview, and which only takes up your 5 minutes of time, and he just wants to see whether you did right or not, and this is the final filtering funnel. And then after that you go back to where you came from, and there will be someone sitting at the reception who is coordinating all of this, so that if guy sitting in the room tries to take a break, then he will halt people at the main gate, and whenever they are ready, he will keep sending more people. Now this looks like a fair strategy, but What's happening here is that until one candidate has come out, you cannot send another candidate, because even though the first guy is taking less amount of time, the second guy is taking half an hour. So if something is taking half an hour, people will keep piling up there and he will not be able to handle the load. And the third guy is also sitting idle for 25 minutes after he has processed the first guy in 5 minutes. So what can be the solution here? You will have one more room in which you will have same 3 guys, and now the receptionist will start sending people in from gate to this room as well. After that, if you get even more candidates, you can have one more room and you'll have 3 rooms doing the same task with same number of people. And the person sitting at the reception will keep sending guys to the corresponding rooms as soon as they come out. But there's a catch here, which I didn't tell you about. The catch is all of the 3 people sitting in this room are all technical people. So first person can take the interview as well. So what's the problem with this approach? The problem with this approach is that the first person and the third person are sitting idle most of the time. So now you are having a very long line at your gate because 3 rooms are still not efficient. What can you do about that? You can do one thing notably that I can see. Suppose this is your input gate. So forget about this, what is spout and bolt for now, and just think of this as your input gate via which interview candidates are coming. So as a solution, what you can do is that only assign 2 people for the first task, who is checking the resume and identity of the people, and then assign 4 or 5 people for the interview process, the main interview process, which is taking so long time, and then assign maybe only 1 person for the last process, depending on how much time that process is taking. So this will be a great solution because now the number of people are dividing. This will be a great solution because you can increase the number of resources where your performance bottleneck is. Performance bottleneck was the interviewing part. So now you have more people there. So this is what Storm is about. You have your input data which you want to process somehow. You can divide it into a small number of steps and define what each step will do. And then you can define the parallelism at each step, that this process only takes small amount of time, only assign 2 threads to this. This process takes longer amount of time, assign 3 threads to this, and the last process is very small, just assign 1 thread to it. And maybe sometimes assigning more number of threads to a particular process might not be easy, because that person might need to coordinate all the outputs so that he can write down which all candidates were selected and he can count that your selected candidate quota is fulfilled or not. Because if you send them to different rooms, you will have to coordinate between them that how many candidates have been actually selected. This is what you will find in these points as well. The work is delegated to different types of components that are each responsible for simple specific task. So this guy's task was just to note down the identities and check the resumes. This guy's task was to take interviews. This guy's task was just to count the number of people that has been selected. The input stream of Storm cluster is handled by a component called spout. So the first guy who is taking people in from the gate and checking the identities and making sure that everyone goes to the right person, this guy is called a spout. So this guy's only job is to handle input data and tag that data if you want to, and then divide that data to the next processes. The spout passes the data to the component called bolt, which transforms it in some way. So now you have bolt, the guy who is taking the interview. You might have second round of interview as well. So you might have more bolts in here and have as many number of steps as you would like. So all those steps will be called bolts, and you can just name your bolts that this is step 1 bolt, this is step 2 bolt, this is step 3 bolt. And all of them are transforming the data or interviewing the data or doing anything that you would like with the data. A bolt either persists the data in some sort of storage or passes it to some other bolt, like we are doing it here. So this guy did not persist anything. The last guy, suppose he checked down whether this candidate was selected or not, and if he was selected, he just saves it down to a database. So this is what all Storm is about. So there are only 2 main components that you need to worry about. One is spout, one is bolt. Right, so let's see what components does Storm have. So the components we just saw that were spouts and bolts, that were from developer's perspective that you need to care about. But now let's see how Storm handles all of the things that you gave him, and how does it coordinate between all of those processes. Think of those machines as rooms that you had in your interview center where you were interviewing the candidates. So each room can have multiple bolts, each room can have multiple spouts, and each room is known as a worker. And there will be a person who is called supervisor who will be sitting in each room and will take care of all the people who are coming in. This supervisor is not one of your bolts, and this supervisor will be a daemon process which is run by Storm just to take care of all of your spouts and bolts within that worker. Storm mainly has 3 sets of nodes. One is Nimbus node, another one is Zookeeper node, third one is supervisor. So Nimbus node is like the receptionist who was sitting at the counter and who was coordinating everything. If any person in any room is on a break, supervisor will let the receptionist know, which is Nimbus, and Nimbus will stop sending candidates to that particular room. In fact, if any person has to go somewhere, Nimbus will send the replacement of that person. So it is the person sitting on the counter who is responsible for everything. So it is like the job tracker that you have in Hadoop. So Nimbus is the guy who uploads computations of execution. So whatever code that you have written, you submit it to Nimbus, and it's Nimbus's responsibility to send that code over to all the supervisors that you have with you. It also distributes the code across the cluster. It launches workers across the clusters. Workers means rooms. And it monitors computations and reallocates worker as needed. So I think you get the idea what Nimbus does. So you don't need to go into too much detail of Nimbus, Zookeeper and supervisor, because this is what Storm handles and you have nothing to do with this. Of course, this type of information can be handy while you're debugging your system. If you don't know what Zookeeper is a central configuration management system. So Nimbus talks to supervisors via these Zookeepers so that even if Nimbus goes down for some time, he knows where every supervisor is running and pick it up where it left the last time. Supervisor read the status of what Nimbus is saying via Zookeeper, and everything they want to coordinate about, they will coordinate via Zookeeper so that you don't miss the state. If supervisor goes down, it should know where your Nimbus is, and when Nimbus goes down, it should know where your Zookeeper is and what state they are in right now. So you have your supervisor nodes which communicates with Nimbus through Zookeeper. So let's see what components does Storm have. So there are 5 things in total that you need to take care in order to write great Storm topologies. So one is tuple. So whenever you are sending a data from one spout to next bolt, each unit of data is known as tuples. So now the interview candidate that you are sending from here to here and here to here is a tuple. And in general, when you're sending the data from here to here, that will be a grouped amount of data. Think of it as a row in a DB or in an Excel sheet. So whenever you will write your topology, you will define the headers that you will be emitting, and then in the subsequent emits, you will keep sending these tuples one after the another. So you will define the column headers first, like first one is A, B, C, D, and in the subsequent requests, you will just send some comma separated values known as tuples, and the bolt will understand that the first value corresponds to A, one corresponds to B, this corresponds to C, and this corresponds to D. So you cannot change the data format once you have declared it. So once you have declared 4 columns, you cannot send 3 columns. Another one is streams. It is unbounded sequence of tuples. So this pipe that you have opened for sending data from here to here is known as a stream. So you can keep sending the data via the stream as long as you have the data. Then you have spouts. Spouts are the guys who are reading the data from outside world. So this is like the gate that you had, and you are getting data from all over the world. People are coming via taxi, via buses, via trains, via their own vehicle. And spout is responsible for taking that data in and sending that data to your bolts. And in real life, you will have something like your logs that are being read by the spout, or your Twitter API, which is sending you continuous tweets. Then you have bolts. Bolts process input streams and produce output streams. as you can see here. They can run functions, they can run filters, they can aggregate, they can join data, they can talk to databases. They have all the power in the world and they can do anything. It's really in developer's hand what you want to write here. You are given a method that is called execute, and you can do anything to the data that you are getting in. And overall, after you have defined all of these steps and defined how they connect to each other, that will be essentially a directed acyclic graph. That thing is known as topology. So the overall calculation represented visually as a network of spouts and bolts is known as your topology. So let's see the use cases of Storm. As we have already seen, Storm is used for real-time stream processing, and there is no need to have queues when sending data from one component to another. So if the second bolt is not able to handle the load, Storm will take care of that itself, and after few of the events have piled up on that bolt, Storm will stop sending data to that bolt instance until all that data have been processed. So that queue is sort of producer-consumer queue. So Storm takes care of handling of the producer and consumer queues between bolts. Of course, it is used for continuous computation. The data you are getting in, you can just keep computing the data, and suppose you are just adding the numbers that you are getting in, you can keep adding those numbers and show them somewhere, maybe on a dashboard as you would like, and you can do all sorts of analytics on that. Sky is the limit really. Then you can have DRPCs. This is a very fine thing that has come up in last few years. And what DRPC is, so suppose someone has called your API and you have a task which is very CPU intensive, like some sort of image processing or something. So instead of doing it on your machine, which will take a long time, you can send your operation to remote Storm cluster, and Storm cluster will parallelize the operation, compute the result, and send the result back to you. So all your CPU intensive operations will be done by Storm in a very quick time. So we have already seen how it can be used in financial, social, and retail world. So you can use Storm to prevent certain outcomes or to optimize certain objectives. So of course you can save security frauds and compliance violations, order routing, pricing. You can optimize your offers. You can judge the performance of a particular offer using Storm and real-time events. And if that particular offer is not doing good, just take that offer out. And you can set your pricing according to the pricing of your competitors. So suppose you are getting the price events of your competitor websites from some stream. You just need to parse that, and whatever prices you have on your competitors, just set the product price of your product according to that. So of course you can have all sorts of functionalities that you see here. You can go with them one by one. I'm pretty sure they make sense from the outset. So what are the key differentiators of Storm that make Storm unique? Well, it is very simple to program, and the complexity of distributing the data and fault tolerance and resilience is all drastically reduced while programming with Storm. You will see how simple it is to program with Storm. And it's easier to develop it in a JVM based language, maybe Scala, Clojure, or Java. But you can basically write your spouts and bolts in almost any language that you would like. So if you have, suppose, a machine learning library that is only available in Python, you can write your Storm and bolts in Python and leverage those libraries. And the most important feature is it is fault tolerant. So if anything goes down, Storm will reassign those tasks to some other node. So you won't have to worry about whether something got processed or not. The Storm technology stack. Storm is mostly written in Java and Clojure, and some of the parts of Java are also written in Python. Storm runs on JVM, and it is written in combination of Java and Clojure. And Storm's primary interfaces are defined in Java, and the core logic is implemented mostly in Clojure. So most of the code that you will be writing in Storm will be in Java. Storm is highly polyglot friendly. That means you can write your spouts and bolts in almost any technology possible, but you cannot skip the Java code. You'll have to define your topology in Java, but you can write your spouts and bolts in almost any technology. Some parts of Storm are written in Python. So all the Storm daemons and management commands are run from a single executable file that is written in Python. So all the command line tools that you will see are mostly written in Python. This also includes the nimbers and supervisor daemons that we talked about in our last lecture, and we'll see that all the commands that you need to manage and deploy your topologies are written in Python. Due to this reason, you need a Python interpreter installed on almost all Storm machines that are used by the Storm cluster. Now let's move into some interesting stuff. Storm has basically two running modes. One is local mode, one is remote mode. Local mode, as the name suggests, is used to run Storm topologies in your local machine. This is generally used at the development time, and you will use local mode for testing almost all of your topologies. Remote mode is the mode where you submit the topology code that you have just written, package it into a jar, and then give it to the Storm cluster that is running remotely, and that will distribute your code on all the nodes and parallelize your data. So local mode, although it can parallelize your data, it will just use one machine, your local development machine, and you don't have to worry about whether this thing will run smoothly on remote or not, because Storm takes care of that for you. So you will be writing a simple Java program, which you will be running just as a simple Java program. And when you give that program to Storm cluster, it will take care of all the parallelism, fault tolerance, and resilience for you. Isn't it awesome? So it takes away almost all the headaches that comes with distributed data processing. So let's talk about the local mode in detail first. So local mode is used for development purposes, and the Storm topology that you will write will be run on your local machine in a single JVM. You can debug your code, you can test your code, and after you are done writing all the code, you can submit it to the remote Storm cluster. In the remote mode, we submit our topology to the cluster, the Storm cluster, which is composed of many processes usually running on different machines, and you can add more machines to the cluster anytime you want, and you can remove some nodes from the cluster anytime you want. And remote mode doesn't show debugging information, so which is why it is considered production mode. So all the debugging information is reserved only for local mode. Now in remote mode, we can adjust parameters that enable us to see how our topology is running in different Storm configuration. However, you can also create a remote mode Storm cluster on a single development machine, and I think it's generally a good idea to do so before deploying it to production Storm cluster directly. It lets you make sure that there won't be any problems running the topology in production mode. So let's create our first Storm topology. In fact, I think before creating the topology of counting words, let's first create a topology of hello world so that we can understand what do you mean by a topology and what are the components that are required in a topology. So let's dive into a live coding session. Okay, so now you will see how easy it is to write your first Storm topology. First, we will write a simple hello world Storm topology, and then we will submit it in local mode. After we are absolutely sure that our topology does not have any bugs and it is outputting what it is supposed to be, we will submit it to a Storm cluster, and we will set up that cluster on our local machine as well. I'm using IntelliJ here, but you are free to use any other IDE like Eclipse. So first we will create a Maven project. So let's create a new Maven project. Click on Maven, select next, just give any group ID that you like, com.test, and artifact ID will be tutorial.storm, next, and our project name will be, let's leave it as tutorial.storm, and press finish. So after our project is created, we need to import Storm. Let's go to web, search for Storm core Maven dependency, go to first link, get the first dependency, doesn't matter which version you get, copy the dependency, switch back to IntelliJ, add the dependencies tag and paste your dependency. I'm also using the presentation manager, which will let you see all the shortcuts that I'm using, so that you can see what sort of shortcuts I use, and maybe you might find some useful ones for your own benefit. Now, since we have imported Storm, we will need to change the scope from provided to compile. So whenever you are using your Storm in your local mode, you will need to provide Storm yourself. That means the scope of Storm core will be compiled. But when you will be submitting this to a Storm cluster, we will change the scope to provided, because in that case, remote Storm cluster will provide it the Storm jar so that you don't have the version mismatch. Now let's create our first spout. So as we discussed, there are two main components of a topology. One are spouts, another one is bolt. We can read the data in the spout from any of the queues like Kafka, RabbitMQ, or a file or a database, or anywhere you want it to read the data from. But right now in our Hello World spout, for simplicity, we will just keep generating the data. So what our Hello World topology will do is that our spout will keep producing some random integers, and then it will pass those integers to next bolt. What our bolt will do, it will just multiply whatever it gets with 2 and then outputs it to the next bolt. But I think for simplicity's sake, we will just write one bolt. Now that bolt can push the data to some database via which you can show it on some dashboard, or maybe you can alert someone based on that. But for simplicity, we'll just be printing the data out of our bolt. Let's create our first Java class. Let's name it integer spout. Now all our spouts needs to extend base rich spout. We will also talk about the hierarchy of spouts in a bit of time, but for time being, all of your spouts need to extend base rich spout. So let's extend it from base rich spout. Let's implement the methods it has got. So now you will see we have 3 methods that we need to override. Let's go through them one by one. So open is the method which is sort of constructor for your spout. You will be passed in the map of your configuration, and you will be passed the topology context, and you will be passed in spout output collector. So anything that you want to produce from this spout, as the name suggests, it will go to the spout output collector. So we need to save an instance of spout output collector. So let's create an instance of spout output collector. Let's assign that spout output collector to spout output collector. And so that's it. We don't need any fancy stuff here yet. Now let's first talk about declare output fields. If you remember in my previous lecture, I talked about tuples. So what a tuple is, basically you define the name of columns at the beginning when your spout is initialized, and in the subsequent calls you just keep emitting the rows. So if you declare 5 column names at first, you will have to emit 5 comma separated value in every subsequent call. So in this method we declare the headers of our columns. So right now, as we discussed, we are only outputting random integers. So what we will do is that we will output a field and we'll name it field. So for example, we will do output fields declare new fields field. So we have declared the name of our output field. It will be field. Now we just need to declare random integers from here. Let's do one thing. Let's emit integer from 1 to 100 and then stop, because we don't want to keep this topology running forever. So just initialize an integer here, index, and let's initialize it to 0. Now what we will do in next tuple. So now your next tuple will get called whenever your previous entry that you emitted is processed by all the bolts. This is like that gatekeeper who is standing there, and whenever your interviewee candidate has returned from an interview room, your gate will be sending the next person. So we emit the next entry by using spout output collector dot emit. As easy as that. So you use the fields class to declare the field names. Similarly, you use values class to declare the values, and we will just increment our index. I think this should make sense. So every time your next tuple is called, it will just emit the new value and increment the index. First time it will emit 1, then next time it will emit 2, then it will emit 3, 4, and so on up until infinity. So let's give this a limit if index is less than 100. Alright, so our next task is to create our bolt. Let's create a new Java class. Let's name it multiplier bolt. Now every bolt needs to extend some sort of bolt. In our case, we will use basic bolt. Let's implement the methods. Now we only need to implement 2 of its methods. In most cases, extending basic bolt will be enough, but we will discuss more about bolts hierarchy so that you can make sure which bolts needs to be extended when. So I think both of these methods make sense. So you will be declaring the output fields just as in spout here, what you will be emitting out of this bolt. In this execute method, you will be writing that logic that you will perform on the tuples that you get in. So this is like the person who is taking the interview. So let's get the value out of this tuple, which was emitted by our spout. Tuple dot. So now you have couple of options. Either you can take things into string and then cast it yourself, or directly take get integer. Now you can access the values by indexes or access the values by their names. So what was the name that we emitted here? The name was field. We can get it via field or we can get it via index. Since we only have one value, let's get this by index. It's easier to get it by index. Let's assign it to a variable and let's name it a number. We need to multiply this number by 2, and now we need to emit this number to the next bolt. And if you don't have any next bolt, it will just be informed back to your spout that this entry was processed. So even though you don't have a next bolt, we will emit this entry so that your spout can know that the entry was processed and it can send the next entry in. So it is always important to emit things out of your last bolt. And if you notice one more thing, we don't need to save the basic output collector like in our spout, because this will be passed in to us in every call. So let's emit. Let's declare the output field that we will be sending. Now that we have implemented our spout and our bolt, let's create our topology. So topology is like a simple Java program in which you will say that this spout will be my entry point. Then after this, my data will go to this. So topology builder will basically create that graph in which you will specify how your data will flow in your spouts and bolts. So let's create that main topology. I know a lame name, but never mind. So this is just a normal Java program. You don't need to extend anything here. Just write public static void main and let's build a topology. So the first thing you need here is a topology builder. So let's create topology builder. Now using this builder, you will set your spout. You can give any name to your spout. Let's name it your integer spout. And this spout name can be anything that you will use later on. This is sort of an identifier for that spout. Let's create your integer spout. Now that you have set your spout, let's set your bolt. Let's name it multiplier bolt. Now you must be thinking that we need to assign these spouts and bolts in sequence so that this bolt knows that I need to get data from this spout. But that's not the case. Actually, you need to tell builder that this bolt will get data from this spout explicitly. And how do you do that? Using groupings. So in groupings, because you will have multiple instances of bolts, you need to tell that what instances of spouts should go to what instances of bolts. So to understand groupings, let's talk about that interviewing analogy once again. So suppose what you want is that you want to send all the candidates whose name starts from A to room 1, candidates whose name starts from B to room 2, and candidates whose name starts from C to room C. Now how will you do that? Or suppose there is some other strategy that you want. You want the spout to send people randomly to any room, whichever has free bandwidth. Or suppose you might have another strategy in which you say people from computer science background should go to room A, people from mechanical background should go to room B. So you can have so many strategies that which candidates should be sent to which room. Similarly, you can have many strategies here in which you can define which instance of bolt should get what data. And you will see how important this is when we build some complex topologies further. Right now, I just want to say, give me random tuples to any of the bolts that you have. So for that, we will say shuffle grouping integer spout. So that means this bolt will get data from this spout in a random fashion. Now, you can also pass in some configurations to your topology at runtime. So this conf object that you are getting here, you will get your configurations here. So this can be file paths or maybe some URLs or the number of threads or anything for that matter. So similarly, you can have this in Bolt. I haven't shown you the method where you will get your configurations, but we will get to that. For now, we will just create an empty configuration. Let's set the debug to true so that we can see what's going on in our topology. Now your topology is built, your configuration is created. Let's submit it to the local cluster. As we talked about, we have two modes in which a topology could be run. One is local mode, one is remote mode. So let's submit our topology to local cluster. Let's create a local cluster. Cluster dot submit topology. Let's give some name. Hello topology. Pass it the configuration and then builder dot create topology. Or this is config. Also, let's put this in a try method. And finally, we want to shut down our cluster. As easy as that. So let's try putting in a sleep for some time so that the topology doesn't finish before it is. And you just need to do this in local mode. You don't need to put a sleep in your remote mode. And so there you go. You have your first Storm topology built. Easy peasy, right? Let's try running it. So let's see what we have. All the spouts and bolts that we have are basically executors. So Storm runs spouts and bolts as executor processes. So you can see the executor that 98 was emitted, 99 was emitted, 97 was emitted, 96 was emitted. Now you can search for integer spout and you will see that it emitted 95, 94, 93 up until 99. And when you search for multiplier bolt, you will see it is multiplying the numbers that were streamed for integer spout with 2 and outputting those numbers. You can also try a cleaner method for testing, like just print these out to your sysout and comment debug logs, and then when you will run it, you will probably see much cleaner logs. So that is a better way to test. Here you go. So you have all the numbers that are outputted by your multiplier bolt. I hope it makes sense. So let's see the course outline that we have. So this course is divided into 6 parts, where the first part will be giving you all the background about big data analytics, and we will see why we need Storm and where does it fit in the big data space. Then we will dive into Storm installations and we'll see what are groupings, and then we'll go to nuts and bolts of Storm. But in case of Storm, we don't call them nuts and bolts, we call them spouts and bolts. And then we'll see what is Kafka and why do we need it, how does it fit into this. Then we will see what is a Trident topology, why do we need it. We'll also see DRPC, and then we will have practical sessions of Apache Storm, which will be self-paced, which will help you to kickstart the process of writing topologies in Storm.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!